Hey, Fizzards. So first off, don't be watching this until you've actually tried the practice exam. Give yourself 30 minutes to do take pictures, upload for the first question, and 20 minutes to do take pictures and upload for the second question. I'm going to start share screen. Okay, I'm going to go through each question. So of course there are multiple ways of explaining. Most of these have multiple ways of explaining. I've gone like, I think the ones that I think most of you will come up with. It's totally possible that you have a valid explanation that went a different route that I just didn't think of. All right, for question one, so we've got identical blocks. They're on a horizontal surface. The surface is frictionless except for CD where there is friction. Block one is pushed with a constant horizontal force. So we've got this plunger applying a force from A to B. And then when it reaches B, it loses contact and then it just kind of slides. And then when it hits E, gets to the point E, it hits this second block and they stick together and continue moving. So part A is saying if we want to give block one as much speed as possible at point B, should the student increase or decrease the mass of block one? So let's think about, there's two ways to go about this. You could think about like your kinematics. We are talking about like a force and acceleration over this distance, or you could talk about energy. So the plunger is applying a force, which is increasing the energy or doing work. I thought about it the first way, so like forces and acceleration. So I said, okay, well, we're still getting the exact same force. It's still the same plunger, right? That didn't change. So I'm still getting the same force, but if I think about F equals ma, if I have less mass, that's going to give me more acceleration. I'll even put F equals ma. Now it says do not manipulate equations. That's okay to just say like, hey, F equals ma, same force, less mass means more acceleration. What would not be okay if it said that was like if I completely derive an equation for what the final velocity is. That's a different thing. So now I'm going to say this means more acceleration, and more acceleration for the same distance should have a greater final speed, which is what I want, right? As much speed as possible at B. So I want to decrease the mass because that will give me more acceleration. In this one, I wrote this question, so just caveat for number one. Same with the rubric, right? I kind of had to decide, should I give 1 point or 2 point for all of these? This easily could have been a 2-point one. It also easily could have been a 1 point. I just chose 1 point. And if you use the first route, as long as you say more acceleration and also decrease the mass, then you get that point. Now, if you thought about it in terms of energy, so here we're talking about the kinetic energy of the block. This plunger would be an outside force doing work. So you could say, okay, well, the plunger is still doing the same force over the same distance, so it's still doing the same work, which means the block still gains the same kinetic energy because work is your change in energy. But if you have less mass, that would mean greater velocity. Totally valid. I would recommend the first one. I think it's just a little bit easier and more intuitive, but the second is totally bad. That one was worth 1 point. B, so we have an equation for the speed at B where D is the distance between the lettered points. Regardless of whether this equation is correct, does it agree with your qualitative reasoning in part A? So in part A, we said if we want as much speed as possible, we would decrease the mass. That means they are like an indirect relationship or on opposite sides, and this agrees. Now, it doesn't matter about F or D, right? I'm not asking whether it's correct. I said, does it agree with what our reasoning in part A? Our reasoning in part A said less mass would mean more velocity, and that definitely agrees. So you have to answer, yes, it does agree, as M1 increases, or you could say decreases, VB would decrease / increase. They do the opposite thing. Now for here, let's say you did part A wrong. Let's say you were like, mass has no effect, it's going to cancel out, blah, blah, blah. You're definitely not getting the point for part A, but then if you on part B, you're like, no, this doesn't agree. I said that mass should have no effect, it shouldn't be in there, then you're good. Or if you said increase the mass for part A, not getting the point on part A, but if part B, you're like, no, this does not make sense because I said as M increase, VB should increase, which the equation does not agree. So as long as it is consistent with part A, you would get the reasoning or the point on part B. Part C was a little bit tricky. So here we are plotting the velocity of block one at point B as a function of the mass of cart one. regardless if the equation or the data is correct, is this graph consistent with the equation? So let's first look. We said as m1 increases, velocity should decrease, so that checks out. That's not the only thing, right? We have to actually look at like how much it increases or decreases by. So let's think about to go from m1 to 2m1. So if I were to double this, yes, it is on the bottom, but it is in a square root, so it should not just be halved. The way this one goes from VB to 0.5, that's being exactly halved. That's not what the equation says. The equation says it would be 1 over square root of 1 over 2, which is not the same thing as 1/2. So think about, if I wanted to get 1/2, you would need a 4 in front of the mass, because when it square roots, that would become 1 over 2. So you would have, the graph should be like at mass at 4m1, that's when it halves. So no, this is not correct. Yes, increase and decrease, it does show an indirect relationship, but not by the correct factors, because if m1 were to double, so become 2m1, then the VB would be root 1/2, not 1/2 VB, which is not consistent with the graph. Here, this one, I made worth 2 points. This is a very like vague rubric because the real ones are vague. I took this like from one that was similar. So as long as you connected the data to the equation, so you have, again, very vague, not entirely sure like what counts as that. And then your second point is like your actual conclusion, like, no, this is incorrect because of this root. It's not going to be 1/2, it'll be root 1/2. Or to get to 1/2 the velocity, you would need 4 times the mass, something like that. Okay, here another student comes up with some equation, and this is the velocity at VD based on the velocity at C, mu, G, and D. Without deriving the correct equation, how can you tell this equation is not plausible? So it does not make physical sense. It's something in here is wrong that we should just be like, oh no, that should not be. And it's almost always like, if this one were to increase, then it should increase and it's not, or it should decrease and it's not, something like that. So let's think about, we're looking at the velocity of D based on velocity at C, mu, G, D. So let's look at our diagram from C to D. This is where we have the friction force. So if I'm coming in with the velocity VC, I know that it's going to be slowing down to get to D. So VD should be less than VC. We should say something, we should check, okay, if I come in with more VC, then that would be faster at the end, right? You come in faster, you're gonna have faster at the end. So that part of the equation checks out, that more VC means more VD. We're good on there. Now let's check the mu. So mu is the coefficient of friction. If I were to increase the coefficient of friction, then I would have more friction force, I'd have more acceleration. This is a negative acceleration because it's friction, right? It's going against. So then that means it would slow down a lot more, which means my final speed should be less. So that does not agree, right? We're saying, oh, actually, if I have more mu, that's going to be greater friction force, so I'll slow down more and not have as much speed at the end. So you only need to, it says, how can you tell this equation is not plausible? We've said why it isn't. There's actually 3 things that are not plausible. So for G, same reasoning, very similar. If I have a greater G, that means I have more weight, which means I have more friction force, more normal, which is more friction force, so I have more acceleration, so slows down more, has less speed at the end. And then similar, not quite the same, D, here the friction force is still the same, but if I have that acceleration for a greater distance, then it will lose more velocity. So you could also make that argument. Again, I put 3 in here that are incorrect, but you only need to choose 1. Now, if there had been a minus sign there, then that would have been okay because you're taking away more, so that would leave me with more, but it had a plus, so or it would leave me with plus. Okay, here you got a point if you are just looking at functional dependence. So if you are trying to say like, oh, even if you made the point like more C would actually be less VD, you would get the point just because you were focusing on the dependence even though your reasoning was wrong. And then the last point is one of these 3 or 2 of them or all of them, you have concluded, no, this is wrong because, and given some explanation of like why. So like actually more U should be less VD. All right, E, we are going through each of the different parts and deciding whether the energy of the Earth Block 1, Block 2 system changed or how it changed. From A to B, so the defining our system is super important. If we have Earth, Block 1 and Block 2, UG, or gravitational potential energy, is included, and then the kinetic energies of the blocks. What is not including is spring potential energy, because I didn't have anything about the spring or the plunger. So in this case, the plunger is an outside force, so the outside force is doing work, and because it is moving to the right and the force is pushing it to the right, that is positive work, which means that the system or the block is going to gain energy. So I said you could say it increases because the plunger is an outside force doing positive work, so the system gains energy. You could also say, well, I am specifically looking at UG not changing and the kinetic energy. From A to B, Block 1 is accelerating, meaning it's gaining kinetic energy, so then the system gained energy. In that case, you're not thinking about it as work, you're thinking about it as like, okay, I'm looking at these three energies, and that stayed the same, that stayed the same, and that one increased, so overall it must have increased. B to C is there was no outside force, that was no friction, no plunger. So here I said there's just no force, so there's no work, which means the energy isn't changing, right? Work is the change in energy. So if I have zero work, I have zero change in energy, it stays the same. You could also, similar to the second one, you could say, okay, we're looking at UG not changing in KE. Well, here there's no acceleration, it's at a constant velocity, so K is constant. I'm going to say because it's constant velocity. 1 point for your reasoning here. D to E, that is where you had the friction. So definitely losing energy because you have negative work on the system, or you could say because your kinetic energy is decreasing, you are losing speed. D to F. So this one is a little bit trickier because if you're like, oh, D to F, there's no outside force, there's no work being done. Totally true, but we do have a collision, and it's a collision where 1 and 2 are hitting and sticking together, and we know that that is an example of an inelastic collision, and we know in an inelastic collision that KE is not conserved. In fact, most collisions you're not going to be conserving energy. That is a conservation momentum, not energy. So for there, I said, okay, well, it means that the system is going to lose energy, so decreases, because when they collide and stick together, we know that K is lost in that type of collision. So something about K is lost in the collision. And then the very last part, it says, instead of sticking together, suppose that Block 1 stopped and then Block 2 goes off. Is Block 2's post-collision or final speed greater when this one stops than when they stick together? So yes, it is definitely greater. You should talk about momentum. So I said, okay, at first they're like sticking together. Now if it stops, Block 1 gives all of its momentum to Block 2. So Block 2 now has more compared to before when they stick together. This one kept moving, so it only gave some of its momentum, so 2 only got some of its momentum. So in the case where 1 stops, Block 2 gains more momentum, so has a greater collision speed. Post-collision. Here I made this one worth 2 points, so applying conservation momentum. So again, like it's always a good, I didn't even say it, but it's always a good idea to explicitly say since momentum is conserved, but I'm definitely implying it when I'm saying like, okay, well, Block 1 loses more, so Block 2 gains more in this case. I am definitely implying that it is transferred from one to the other, so that is good. And then your correct conclusion, I'll say conclusion with correct explanation. Okay, Q2, our paragraph length response. So here we've got a hoop and a disc of equal mass and equal radius, and they have the same translational speed. They both encounter the same ramp and roll up before falling back down, reversing directions. Which object reaches a greater height on the ramp before reversing direction? So I bet everyone here is thinking like, okay, it has to do with I, rotational inertia, because that's really the only thing different between them. Remember, rotational inertia is about how far your mass is from like the center. So if I have the disc where it's everywhere, or I have the hoop where it's all on the outside, not the hoop, the ring. Oh, I called it a ring. Oh, sorry, I changed it from a hoop to a ring. Let's call that. It doesn't matter. You can use those interchangeably because I called them both here. So the hoop or the ring has a greater I. So you got a point for just telling me that the hoop has more I and Y. So something about like its mass is farther away from the center, or it's more spread on this outside than the disc. Something about like mass farther away. Now, I would definitely be thinking about energy here because we are going to be rolling. So we've got the kinetic, rotational and translational, and then it's going up a ramp, which means I'm going to like a certain height, right? So that's going to be going to potential. So we're definitely thinking conservation of energy. So let's think about at the bottom, they both are rolling without slipping. So they've got the rotational and the translational. Translational kinetic energy is 1/2 mv squared. It says they have the same mass and they have the same v. So that means they have the same translational kinetic energy. So that is your second point. It doesn't have to be in this order, but somewhere saying like they have the same translational. And your reasoning is just same mass, same velocity with 1/2 mv squared. Now let's talk about their rotational. So rotational kinetic energy is 1/2 I omega squared. We know that the hoop or ring has more I. A lot of people in the call were like, oh, omega must be less. That is if you knew, like if you're like, oh, they must have the same angular momentum. If this increases, this decreases, which is valid, except that this is not a conservation of momentum. You're trying to say that the disc and the hoop must have the same angular momentum. Not the case. If I have like one object from before to after, the momentum has to be conserved. It has to stay the same. But two separate objects do not have to have the same angular momentum. So don't try and use angular momentum between two objects if it's not like a before and after scenario. And actually, we know that omega, the rate at which it's spinning, is going to be the exact same because they're the same radius going at the same speed. So if you think about, I have two wheels that are the same radius of the wheels, and they're going forward at the same speed, there's no way that one is like rotating faster than the other because they're going forward at the same speed and they're the same size. You could use the relationship that omega is v over r, or v equals r omega. It's the same thing. And you know that velocity and radius are the same, so omega must be. But you don't have to explicitly say that. So that means they have the same angular velocity omega, but the ring has more I, so the ring has more rotational kinetic energy. So that would be your third point. And then your fourth point is the using conservation of energy. So you're saying, okay, well, they have the same K translational, but the ring has more rotational, so then the ring must have more in total, right? If you have two things and this one is the same, but this one, one has more, then this one has more total. That was a weird way of explaining that. So the ring has more total energy at the bottom, which means when it goes up, it'll have more potential energy, so it'll go higher. So that one, right, you wanted, your fourth point is basically using conservation of energy. You don't have to explicitly say it, although it is a good good practice. I actually put it in parentheses this time. That was good. But something about like I have more kinetic at the bottom for the hoop, so that means it will transfer to more potential at the top, so it'll go higher. The fifth point on this, so and this is like all paragraph length responses have this like paragraph point. So let's say you made the mistake early on of saying that the disc has more I, but then your reasoning totally follows. You're still going to get this last point because you were like following through. You're like nothing inconsistent, like logical. It's kind of a vague point. Or maybe you used conservation of angular momentum and said like, oh, this one has less omega, so blah, blah, blah. So that you made like one mistake, but you follow through, even though your reasoning is completely off, but you follow through, you can still get this last point, as long as you are doing kind of good physics and kind of makes sense. And then the last one, which one experiences a greater angular acceleration? So I thought about like my equations for angular acceleration. I looked at the torque equals I alpha. I guess I meant to put an explanation here. Okay, so we know that they're going to have the same torque because they're on the same surface. They should have the same friction force with the same R, and torque is RF. So they're going to experience the exact same torque, but the disk has less I. So if you have the same torque with less I, that will mean greater angular acceleration. So the disk, because it has less I with the same torque, will have more acceleration. So very similar to like our first one, we were like, oh, same force, less mass goes with a greater acceleration. Same here, but for torque and angular acceleration. The other way, and this is absolutely valid, is if you're saying up above that the disk is the one that stops first, that means that it came in with the same initial velocity, but it slowed down first, so it slowed down at a quicker rate. It must have had a greater acceleration because it changes velocity in the same velocity in less time. So you could make some argument, and even if you said the ring, right, the ring was the one that slowed down first, then you could have made that same argument as long as you're like kind of consistent between parts. This part is worth 2 points. So if you went the first route, like something about the same torque, less I is more angular acceleration, you have gotten the 2 points. Or this second, I guess, method or reasoning will work as well. All right, I highly recommend that you guys spend some time in the weekend or the beginning of next week going through. I posted like optional, they're small free response. They're not like a full FRQ. It'll be like a little bit like a paragraph length response, but maybe a little shorter, that I put the answers and the like rubrics for. I think those are good practice on the like physics content side of things. All right, bye guys.